All right, good morning, everyone. Today we're going to wrap up chapter 4. I see online that several students have started the homework. Most of it, as I mentioned on Wednesday, is short answer questions based on concepts. And so students shouldn't have any problem answering those questions. And then today we'll cover the examples, and then the homework I've already made due Sunday night. And then Monday we'll have a quiz, most likely based on chapter 3. All right, so let's continue from where we left off. And that should be right around here. Let's see, share. Okay. Section 2, and it should be here. Okay, I believe we stopped right here. Okay, we looked at the equations for the natural response for both RL and RC. And now we look at the step response or the forced response, meaning when we connect an external source to the circuit, we'll derive the expression for that period. Okay, so, and this will go by a little faster or quicker because it's pretty much the same procedure as for the natural response. We have here an inductor, so it's an RL circuit, and we're applying a voltage source Vs, which causes a current I to flow through that circuit. Because it's a series connection, the current I is the same for all components. So I flows through the voltage source, also flows through the resistor R, and the inductor current is also I. Now, when we do this analysis, we want to determine or derive an equation for I of t or IL of t. In this case, of course, because we are talking about a series circuit, the inductor current IL is the same as IR. Okay, so the initial conditions, well, it depends on the initial energy of the inductor. I0 plus, meaning the time right after the switch is flipped, will have the same value right before the switch was flipped. The current through an inductor cannot change instantaneously. So right before and right after the switch is flipped, the current remains the same. The switch was open prior to t equal to 0. And at t equal to 0, the switch closes. So it provides a pathway for the inductor to receive the energy or the charge from the voltage source. We apply KVL at the top. Yes. Yes. Nothing is mentioned about the initial charge. And usually if nothing is mentioned, then you should always take the component to be fully discharged, meaning the energy is completely 0 for inductor as well as capacitor. So if it's explicitly stated that it has some energy, then you use that. Otherwise, you just assume it to be 0. Now, in this case, we will take it into account. So we apply KVL at the top. In the natural response circuit, left-hand side of the equation was 0. Here, of course, we have a voltage source. So the total energy supplied by the voltage source is absorbed by the resistor and the inductor, right? So the voltage that it caused, the voltage drop from that voltage source is across the resistor VR and then across the inductor VL. So when we apply KVL, we obtain 3 terms, not just 2. And so when we derive the solution for this differential equation, we obtain an extra term right here, which is also in terms of the final value. Okay, so the expression is very similar to the natural response expression, except we now have an extra term, which is the final value of that component. And that's IF. So the F notes final. Final value. 0 or I represents the initial value. And as I just stated a few seconds ago, if it's not stated, you can assume it to be 0. Okay. So the equation for I of t is IF plus I0 minus IF. And the exponent remains the same, e raised to minus t over tau. And the time constant also remains the same. Okay. For RL circuits, if it's charging or discharging, doesn't matter. The tau remains the same. Same for charging and discharging. It's L or R. That does not change. Now, the reason I specifically chose a voltage source is to point out that you could transform it. And again, the concept comes from Thevenin and Norton equivalent circuits. The current value I can be given from Ohm's law. I is V over R. And so I can derive the final value for IF from the voltage source Vs and the resistor R. Okay. If this was a capacitor, and we'll see this in example 3, you could flip it around. Given a current source, you can find the voltage by applying Ohm's law. Or by doing, in other words, you're doing a source transformation. Yes. R equivalent, yes. And we'll see that in the examples also. Yes, that is correct. Not always so here's the thing. So in real life, inductors have a descriptive quantity that describes the quality of that inductor. And it's known as the Q factor, Q for quality, which in electrical engineering, Q is also for charge, but that's lowercase and this is uppercase Q for an inductor. It notes the quality of that inductor. The quality of the inductor has to do with the resistance in the denominator. And so if the resistance is 0, quality is infinite. Make sense? Typical real life inductors with high quality will have resistance on the order of like few ohms, 5 ohms or less, not more than that. So we have high quality inductors in the lab, but we use low quality ones just to actually show students how it affects the circuit. And so we'll do that. We'll do the same for lab 6 also. We'll use the same inductors. Taking that one step further, all of the analysis we do in class is theoretical, meaning the components are ideal. So the inductors, the resistors, the capacitors, they're all ideal. And so the resistance for an inductor in the theoretical class is always 0. All right, where was I? Oh yeah, IF plus I0 minus IF, right? So this equation takes into account both the final values and the initial values. Actually, let me not use I. The reason I don't use I for initial is again, because I is for current, so sometimes that gets confusing. And so I prefer to use 0, right? 0 is the time we begin our analysis, the initial point. So the final and the initial values are taken because if the inductor already had some charge stored in it, we can account for it using this equation. So if the problem statement, for instance, mentioned the inductor was charged to like 2 volts, or it had 2 amps of current flowing through it, then you can simply take that value and plug it into this equation. I0 would be equal to 2. Make sense? Let's take a 10-second pause. Let me know if you have any questions. And again, if students are interested in the derivation, I do have, I can explain. If you come to my office, I can explain to you if you are interested. I can show you the derivation. It's available in many electrical engineering books. It's also available on many sources on the internet. All right, any questions? Okay, then let's move to step response for an RC circuit. Same principle, same concept. Here I'm using a current source instead of a voltage. And again, the reason is to show students that you can solve the circuit for either a source, for either a voltage source or a current source, does not really matter. You would simply use Ohm's law to transform that circuit. So here, prior to t equals to 0, the switch is open. At t equal to 0, the switch is closed. And so the capacitor has a path to charge from the current source IS. Okay, capacitor starts charging. VC eventually will reach a value that is equal to the current source times R. Okay, the final value of VC would equals IS times R. Since nothing is stated, I can say V0 is 0 volts. But even if it was, we would still take it into account in the equation. Okay, same thing. We apply KCL. We obtain a first order differential equation. And in that natural response, the left-hand side of the circuit would be equal to 0, or not left-hand side, but one side of that circuit would be equal to 0. In this case, it is the current source IS. And so we obtain one extra term in our expression, and that would be VF. If you notice, it has the exact same form as the RL circuit, right? IF plus I0 minus IF. And here we have VF plus V0 minus VF to e raised to minus t over tau. Same function, everything remains the same. Tau is also the same, R times C. Then again, voltage is given by Ohm's law, product of the current source and the resistance, IS times R. All right, any questions? We'll take a 10-second pause and let it sink in. And we'll look on the next slide and a couple of slides after that, we'll look at what that equation represents and how we can use it for both natural as well as step responses. Any questions before I move on? Okay. So looking at all four equations for both natural step response for RL and RC, we can come up with a general solution for first order circuits. Okay, because the equations have all are, I wouldn't say the same, but they're all similar. They all have a similar structure. They all have a similar form. So you can use this one single equation to solve for all four circuits. Okay, where x of t, x is a quantity. That quantity can be either voltage or can be current. Okay, x of t can be given by xf plus x0 minus xf into e raised to minus t over tau. Okay, x is a quantity that can stand for current. It can also stand for voltage. Okay, f and 0 represent final and initial values respectively. So xf is the final value, x0 is the initial value. And then e raised to minus t over tau, that remains the same. T is the variable function of time, right? So t is that variable, and tau is the time constant. So now let's take a in-depth look at how this equation would work for both applied step response as well as a natural response. Okay. So let's say we are talking about a natural response circuit. Okay, natural response means the component is charged and it's simply discharging all of its energy down to zero. So in that case, what would be our final value? Natural response, stored charge, source is removed, then the energy is just being discharged. What is the final value? Natural response, energy is being discharged completely. What is the final value? Zero. So you plug in XF is equal to zero. What do we get? So it's natural response, XF would be zero. Whether it's volts or amps doesn't matter. So the expression X of t simply becomes X0 times e raised to minus t over tau, which is the natural response equation. Remember from Wednesday, right? It's a natural response equation. V0 into e raised to minus t over tau, or I0 into e raised to minus t over tau. Does everybody see that? So this expression works for natural response circuits also. And the reason I would strongly recommend students use this equation, again, all equations are the same. They have this, they have the exact same structure and form. In this class, of course, we won't delve with multi-level steps in a problem. In EE classes, we do that. Like, a component might be fully discharged, then it will start charging to a certain level. Then it moves to a second position where it discharges to a certain level, but it does not discharge all the way to zero. And then it starts charging again, and then discharging, charging, discharging. It does not go all the way to zero. And so that's where this expression would be very handy, because the final value and the initial value would never reach zero. If you have taken the lab, you might have noticed when you increase the frequency for the capacitor charging in lab 5, your triangular waveform, the capacitor charging waveform, did not reach the max. It was much lower than the max value. Does anyone remember that? You are applying a square wave, and when the frequency is small or low, frequency is low, meaning the input waveform is not switching as fast between zero and max. So the capacitor is able to charge to its max value and discharge to zero. But if the frequency is increased, meaning the input is switching at a faster rate, then the capacitor does not have time to reach full charge. It does not have time to reach zero. So in that case, our initial and final values are something different. They are not zero. Okay, so you have to take those values into account. Does that make sense? Okay. All right, so the rest of the steps remain the same. You redraw the circuit, you find the equivalent circuit by reducing all the components down to one single element. You identify the variable, which is current for an inductor and voltage for a capacitor. Determine the initial conditions, find or determine the values for X0. If it's a step response, find the value for XF, final conditions. And then find the time constant and directly plug into the equation and write down the solution. And that would be it. So again, the steps remain the same for all 4 circuits. What you'd have to do is identify the problem statement, extract as much information as you can, find the values for the initial voltage current, find the final values for the voltage and current, calculate tau, and then plug it directly into the equation. Okay, so the equation is already provided. You have to know how to use it. And that comes from chapters 1 and 2. Okay, circuit analysis, chapters 1 and 2. All right, any questions before I move on? Okay. When you plot the values of t with respect to the time constant tau, if t is equal to 1 tau, 2 tau, 3, 4, 5, and 6, you get a curve that looks like this. This is for charging. And this is for discharging. In discharging. Okay, it's a universal time constant chart. Doesn't matter how big or small the inductor is or the capacitor is, this never changes. All equations include the exponent. And so all curves or all graphs or all charts relating to transient analysis will always, always, always have this form, will always have this shape. Okay, the only thing that changes is the value, but everything else remains the same. And the values for the time constant chart will also remain the same. If it's charging, you know, it's e raised to minus t over tau. So it's e raised to minus 1. E raised to minus 1 is 0.37 or 0.368. Okay. So when it's charging, it charges all the way up to 63.21% of its max value. If max value is 10 volts, it's going to charge to 6.321 volts. So it acquires more than half its charge or more than half the energy within the first time constant. And conversely, when it's discharging, it loses more than 63.21%, not more than, but it loses 63.21% of its stored energy within the first time constant. Okay, so when it's charging, it acquires more than half. When it's discharging, it loses more than half within the first time constant. And then, as I stated, you know, early on in this chapter, it's a mathematical equation. So you could plug in t as any mathematical value, really large value, and you would still obtain a number. But it does not mean that that's still remaining, right? This equation is simply an approximation in that sense. It will never reach a finite zero. So we put a stop to it by generally accepted convention after 5 times tau. So the value is more than 99%. When it's charging, it acquires more than 99% after 5 time constants. When it's discharging, it has already lost more than 99%. And so after 5 time constants, we say that the capacitor or inductor has either reached full charge or reached full discharge. Okay. And again, even though mathematically we never say it reaches full zero. All right, 10-second pause. Let me know if you have any questions. The general solution slide is the most important. Okay, because that works for all 4 circuits. All 4 circuits. Any questions before we move on to examples? Okay, let's look at example 1. Explicitly stated here is that the switch has been closed for a very long time. So the switch was closed for a very long time. I'll first draw the circuit for time t less than 0. So let's look at the circuit. Current source, resistor, 1, 2, 3, 4 resistors, and 1 inductor. And we are told that the switch has been closed for a long time before it is opened at t equals 0. right? Before it's opened at t equals 0. So if I draw the circuit for t less than 0, and again, usually I draw this just for my own understanding. So students, I would advise, or I would suggest that you also do the same. Sometimes students like to skip, which is fine. If you're confident in your own abilities, that is absolutely all right. So I have an inductor like this. I have a resistor like this. Okay, switch has been closed for a very long time. What do you expect the inductor to be? Remember, a very long time indicates the component is at steady state. So if it has steady state, sufficient time has elapsed for the inductor to reach full charge. So how can I represent the inductor? As a short, right? As a short circuit. I can represent the inductor as a short circuit because the inductor has reached full charge. So my circuit actually becomes like this. If it's a short circuit, all of the current is going down that path, right? A short circuit means all of the current flows through that component. Nothing is going anywhere else. The resistors are all bypassed. And we are not analyzing the circuit before time t equal to 0, right? We don't care about what happened in the past. The only thing we care about is it's been closed for a very long time. So the inductor is at steady state. It's a short circuit. All of the current is flowing to the inductor, meaning IL should have a value equal to the source IS. In this case, 20 amps. Again, all of the current is flowing through the inductor. Does that make sense? Similar to the similar to the time constant concept, I like to state that more than 60% of your problem is solved in the first setup. Okay. The analysis is the main part. The equation is simple. You can simply take the values and plug it in, but trying to find those values, that is the main portion of your solution. Does that make sense? If you don't set up the problem correctly at the beginning, if you do not understand it correctly at the beginning, the rest of it does not matter. So again, more than 50% of the problem is answered in the first initial setup. So again, redraw the circuit for time t less than 0, and then redraw it again for time t greater than 0. Okay. So this is t less than 0, and I did remind that IL is equal to 20 amps. Now, when the switch flips open, what happens? For t greater than 0, greater than or equal to 0, the switch is flipped open. I have the inductor, 2 ohm resistor, 10 ohm resistor, and the 40 ohm resistor. Okay, 40 ohm resistor. So now, what kind of a response is this? Step or natural? No source means a natural response. The inductor is now simply discharging. Keep track of the current direction. IL is given to us as going down. Okay, so we do not change the given direction. The answer could turn out to be negative, but that does not matter. We have to keep or stick with the direction that is given to us in the problem itself. So it's a natural response problem. Which resistor is it using to discharge? Simple question. It's either 2 ohms, 10 ohms, or 40 ohms. All of them. Discharges through all of them. If it's present in the circuit, then it's part of the circuit. The inductor discharges through all of them. And so here, we need to reduce all 3 resistors down to one single resistance. And that would be finding Req, determining Req as seen by the inductor L. Okay. Find Req as seen by the inductor L. So you remove the inductor L and you find Req from these 2 terminals. So we start at the farthest end away from the measurement terminals. And I can write Req is 40 in parallel with 10 plus 2 ohm resistor in series. 40 in parallel with 10 gives me 400 divided by 50 plus 2. And so my Req is 10 ohms. Req is 10 ohms. Initial value of the inductor current was 20 ohms. I'm sorry, 20 amps. After the switch is flipped, IL at 0 plus, right after the switch is flipped, should be equal to IL at 0 minus. And so I can write my initial value of the current I0 is 20 amps. And because the switch is closed and the inductor is discharging, I can also write IF, final value is 0. It does not state anywhere in the problem that the discharge is interrupted. Again, for this class, for non-EE majors, I do not do those kind of problems. We do those class, right? Sometimes the component is large enough, it's discharging at a slow rate, and before it can reach 0, we start charging it again. So that's when final value would no longer be 0. In this case, we simply assume it discharges all the way to 0. Final value of IF is 0. So I can directly write down the solution for IL of t as IF, the final value, plus I0. Again, remember, this is not O, it is 0. Minus IF e raised to minus t over tau. Plug in the values. IF is 0. I0 is 20. Minus 0. E raised to minus t. Oh, forgot to find tau first. Tau is L over Req. Inductor value is given as 2 Henry. So 2 Henry divided by 10, 0.2 seconds. And so T divided by 0.2. And finally, I can reduce that expression and write IL of T is 20 into E raised to minus 5T amps. Do not forget the units, okay? The quantity is still current, I of T, right? The equation is describing the current for the inductor. So the unit is always amps. And this equation is valid for time t greater than or equal to 0. All right, think over this. Let me know if you have any questions while you write it down. The first step was to draw the circuit for time t less than 0 and time t greater than 0, is right here. That allows me to establish the inductor current prior to the switch closing. And so that sets up what is okay. So that sets up the inductor current to be equal to the source current, 20 amps. And then once the switch is closed, the inductor starts discharging to all the resistors. Since there are 3 of them, we find Req as seen by the inductor. And we find tau, L over Req, 0.2 seconds. So we established I0, we established IF, we established or calculated tau. We simply plug it into this equation and we obtain our answer. Does the method make sense? Any questions? Any questions at all? And again, I repeat, once you have the values, it's easy to simply plug it into the equation. So most of your, a major chunk of your problem is the setup, right? It's the setup. And for that reason, I would strongly recommend that students draw out the circuit for time t less than 0 and time t greater than 0. And then it calls upon all of your analysis expertise from chapters 1 and 2. Okay. All right, questions? Any questions before I move on?
Like time greater than 0, the circuit that you drew, is it always going to have no source, or is it just for analysis?
No, from the facts that are given to us, there is no source after time t equals 0. So it's just open. Yeah, it just stays open. A follow-on question might be like after 5 seconds, the switch closes again. And then opens again at like 2 seconds. Closes again after 2 seconds, opens again after 2 seconds, and then so on and so forth. And so that's like a real life situation where engineers sit down and design circuits based off of that information. But just the facts given to us in the problem itself, the problem statement, it simply opens up and that's it. It doesn't talk to us about, you know, what happened before or what happens afterwards. Okay, so let's go into the second example. It's very similar to the first one, but this time we have a capacitor. So switch has been in position X, meaning on the left side, for a very long time. And again, when you read the words long time, it simply indicates capacitor is at steady state. At steady state, capacitor has sufficient time to reach full charge, and it's now behaving as an open circuit, right? So I'm going to draw the circuit for time t less than 0, and it simply comes out to be a voltage source along with a resistor and then a fully charged capacitor. And because the voltage source has a polarity with a plus on top, my capacitor voltage VC also is polarity plus on top. 10 kilo ohms. 10 kilo ohms. Okay, so when switch is on the left, capacitor is fully charged with a value equal to the source voltage, 100 volts. For time t greater than or equal to 0, the switch is flipped to the right, and now the source is disconnected. I have a fully charged capacitor connected to 3 resistors and no source. And since there is no source, I expect this to be a natural response circuit. And again, I want to reduce this to find Req as seen by the capacitor. And Req in this case would be, starting in the farthest end, $60 kilo ohm in parallel with 240. And then in series with 32K. And this gives me an Req of 80 kilo ohms. Do not forget the unit prefix, very important in this case. It's not 80 ohms, it's 80 kilo ohms. Okay, 80 kilo ohms. From here, I can establish the initial conditions also. VC at 0 plus would be the same as VC at 0 minus, which would be 100 volts. So I can write V0, voltage at the initial starting point of analysis, is 100 volts. And because it's a natural response problem, Vf is 0 volts. Time constant tau is simply Req times capacitor C. And so it's 80 kilo ohms times capacitance value is given as, what is it given as? 0.5 microfarads. 0.5 into 10 raised to minus 6. So tau comes out to be 10 raised to 3, 5 8s are 40, point gone, so 4 milliseconds, right? 4 milliseconds. 4 milliseconds. And finally, I can write down the expression for capacitor voltage Vc of t as Vf plus V0 minus Vf into e raised to minus t over tau. You plug in the values. Vc of t, final value is 0, 100 minus 0, e raised to minus t over 0.04. And that gives me what? 0.04 reciprocal 25. So Vc of t is 100 times e raised to minus 25t volts. And this equation is valid for all time t equal or greater than 0. Very similar to the previous one. All right, questions? Do the steps make sense? Yes or no? Okay, then one thumbs up. All right, we have about 5 minutes remaining, so we can move on to the last one. Now, this one is a step response because it has a source at time t less than 0. This is just to show that the capacitor was fully discharged, okay? In real life, obviously, we do not want a situation where a source is completely short-circuited. This is simply to show that the capacitor is not part of the circuit. Right? In real life, you do not want a source and the short circuit the output terminals. Make sense? Right? This is just to show that the capacitor was fully discharged for a very long time. C is fully discharged. And so VC at 0 minus is equal to 0 volts. And then time t greater than 0, the switch is flipped open. It is simply showing the current source is now connected to the capacitor. And it starts charging. Since the current is flowing in a clockwise direction, the voltage will have a polarity as shown in the figure, plus at the top, minus at the bottom, and this would be VC of t. And that's it. The only thing we include here is our initial and final values. Initial value, of course, VC at 0 plus would be equal to VC at 0 minus, which would be 0 volts. Does not state that the capacitor had any charge, but that's the purpose of showing the switch. Because of the switch, I can infer that the capacitor was fully discharged to 0 volts. R is 2 kilo ohms, so my tau is simply R times C. 2 kilo ohms times 10 microfarads. So my tau is 20 milliseconds. Right? So far, so good. Now, we need to find what the final value is. It's a step response, remember. And there is nothing else given in the problem statement. It doesn't say that at 5 seconds after time or 5 milliseconds, it's interrupted. So if nothing is stated, we simply assume that the component will charge to the source level. Okay, but the source is a current source. So if you wish to find the final value of VF, we would simply take the current source. It would be I times R, and I in this case is the 10 milliamp current source times the resistance, and my final value of VF would simply be 20 volts. Okay, 20 volts. And so I can directly write down the solution for VC of t. VF plus V0 minus VF e raised to minus t over tau. And therefore, VC of t is 20 plus 0 minus 20 into e raised to minus t over 0.02. VC of t is 20 minus 20 into e raised to minus 50t. This would be volts. Expression is valid for all time t greater than or equal to 0. So again, initial conditions imply that the capacitor was fully discharged. So initial voltage across the capacitor is 0 volts. So V0 is 0. VF, the final value of the capacitor voltage, can be determined by applying Ohm's law. So VF is the current source, 10 milliamp current source times the resistance, 2 kilo ohms, gives me a final value of 20 volts. Time constant is simply RC, 20 milliseconds. Take all three values, plug it into the equation, and we obtain 20 minus 20 into e raised to minus 50t. All right, questions. The steps make sense. So again, all three examples are similar to what you would see on the exam. Okay, you might just have to think for a few minutes, but rather, there won't be any tricks or twists or turns. Yes.
The quiz that we have on Monday, is that on transient stuff or is that on, trying to remember what we missed because we didn't have a quiz this week?
No, chapter 3. Capacitors and inductors.
Okay.
So I will post an announcement after class is done. I post announcements every Friday evening. Regarding the quiz, I post every Friday evening. Yeah. But it will be on chapter 3. All right, so we'll end class here today. I'm available for questions. But for now, I'll bid you a good weekend and I'll see you all on Monday. Again, homework is due Sunday night and quiz on Monday based on chapter 3. All right, let me stop this recording.